In a previous talk, which I've linked to in the notes below, I described a new persistence model that I've been developing for Java based on multiple heaps. The idea is that once a Java program is running, it can create, populate, and save additional heaps of objects, and these saved heaps can then be attached to other running programs which can reuse the objects, all without having to write the usual code to serialize or otherwise externalize them. That's a quick summary. To hear a more detailed explanation of the persistence model, take a look at the linked talk entitled Are Many Heaps Better Than One? My implementation has been progressing nicely, and today I'm going to give you a short demo. This prototype doesn't use non-volatile memory, although that may be something to try later. For the demo, I'll be using a Dell 7420 laptop running Linux with 32 gigs of memory and a 500 gig SSD. ptable is the small demo command line application. Using one command, I can create a heap containing a table, populate that table with random data, and save the heap to a file. The code looks roughly like this. I've simplified it for this slide to avoid unnecessary clutter. Using a different command, I can attach a pre-built heap and make random changes to the table before checkpointing again. Other commands can be used to print some stats or the entire table. Note that the table contains a standard java.util.TreeMap. Let's move to a terminal. From this code, I made an executable using my experimental version of GraalVM native image. First, I'll make and save a heap containing a table with 60,000 entries. The lookup keys are random longs, and the associated values are the string representations of other random longs. Let's look at some size statistics. The size of the heap and the size of the checkpoint file are both about 10 megabytes, as this is a 64-bit JVM. Once we have a pre-built heap, I can use a different subcommand to attach the heap, make a number of random changes to the table, and then checkpoint the modified heap to a new file. Each change swaps the values associated with two randomly selected keys. Here are the original and new files. I'll print and compare the two tree maps. As you can see, there are indeed the right number of differences, namely 128 from 64 swaps. Okay, so you get the idea. I should also mention that in this system, checkpoints are failure atomic. You can't get a partial checkpoint. Now I'm going to do the same thing, but on a bigger tree map. I prepared the heap file earlier. That took a little longer. A look at the size of the table explains why. That heap is 1/3 of a terabyte, and it's being attached, modified, and checkpointed in under a second. Incidentally, that's as big a tree map as you can make in Java 8, having almost 2 to the 31 entries. Comparing files of 1/3 of a terabyte usually takes a while, but using my special version of comp, I can verify that there are indeed roughly the expected number of changes. Each change alters two 8-byte pointers, and metadata differences account for the excess. Okay, that's all for this demo. If you want to know more about the persistence model, take a look at the talk linked to below, although I should mention that some details are already out of date. And if you'd like to know more about how this prototype works, follow me on Twitter, link below, where I'll be posting pointers to explanatory blog posts as they appear in coming weeks. Thanks for watching.